Hello everyone, welcome to your sixth lecture in historical geology. This is Dr. Hurt, and we are going to be talking today about a very important subject that you're going to want to be very familiar with, and that's on sedimentary rocks. Now, so much of Earth history that we know about comes from sedimentary rocks. So much of the information we have, what's its origin? Sedimentary rocks. So you need to know this stuff. This is really important. And I can just tell you, you got to kind of buckle down for this lecture. It's kind of long, and there's a lot of information to it, but it's all stuff you need to know. So pay special attention. This is going to be important stuff. It's going to be on your test in a big way, and you need to know it. So I think I've made my point, and we'll just get right on with the lecture material. So you're taking a look at beautiful Bryce Canyon. This is a national park in Utah, and all these kind of structures you can see here are formed from kind of differential weathering of the sedimentary rocks that are around. And you can kind of see, hopefully, you can see very clearly in these beds that are rather continuous through these pinnacle-like structures, right? So you can see the white layer here. You can see the different layer. You all see the different layers here, right? You all see the different layers here and here and here. So sedimentary rocks form in layers. That's a big part of what they do. So, and what makes a sedimentary rock? So let's get into this right now. We talked about igneous rocks last time. Now we're talking about sedimentary rocks. So sedimentary rocks are made up of weathering products. They're made up of sediment that have been cemented and glued together to make a rock. Okay, they provide, the reason they're so important for us is because they provide a record of past environments of Earth's surface, and they contain fossils too. They're the primary rock to contain fossils. So that's how we know about life, how life has changed through Earth history. That's the primary means that we know about what the environment was like in other parts of Earth's history. So it's very, very important for y'all to know this stuff. Now, sedimentary rocks are a thin layer that cover the Earth. Okay, so you know the Earth's crust is mostly igneous and metamorphic rocks. Okay, you'll see that there. But there's this thin layer of sedimentary rocks that are on top, and they cover about 75% of the Earth's surface. So a lot of the Earth's surface is covered with sedimentary rocks, but by volume, sedimentary rocks make up a very small percentage of Earth's crust, right? Earth's crust is mostly igneous and metamorphic, mostly igneous, but you have this kind of veneer or skin of sedimentary rocks on top. Now, the reason that sedimentary rocks are so important is because they record a record of what Earth's environments were like in the past. So if you think about different environments today, you'll quickly realize that different kinds of sediments or materials are laid down, right? So for example, if you go, very famously, if you go to the beach, you go to a coastal environment, what kind of sediment do you find? I'm sure you all know this very clearly, right? What kind of sediment do you find? You find sand, right? Beach sand. Okay, so that's one kind of sediment that's laid down in a very specific environment. It doesn't matter if you go to beaches in Greece or beaches in Corpus Christi or beaches anywhere, you always find the same thing. You always find sand, right? So it's a very common coastal sediment that's laid down. There's something special about that depositional environment that lays down sand, okay? Think about when you go to a desert. What kind of sediment do you find? Also, a lot of times in deserts, you find sand, right? So what about if you go to a lake? Think about this. If you go to a lake and you walk into a lake or walk into a pond, does it feel nice between your toes when you walk into pond water? Okay, usually no, right? It feels kind of squishy and terrible. Right? Have you ever walked barefoot into a pond or maybe a small lake? It feels kind of squishy and terrible. Okay? It's because the kind of sediment that's laid down there, instead of sand, it lays down clay and mud. So it doesn't feel good to walk in mud. You know, it's squishy. and kind of slimy and gross. Okay, swamps lay down different kinds of sediment. All right, and they actually lay down, very famously, they lay down coal type sediments that eventually become coal. Okay, so deltas lay down things that are kind of silty and sandy, and sometimes they are muddy. Okay, but the point is I'm trying to make here, without going through all the details, is that the kind of environment is going to lay down different kinds of sediment, and that kind of sediment is going to tell us, it's going to eventually become a rock, and it's going to let us know what the environment was like in the past. Okay, it's very important. Sedimentary rocks, right? So record your environment, right? Sand dunes become sandstone, right? Carbonate reefs eventually become limestone. So coral reefs like this grow into turn into limestone eventually when they're buried and lithified. Okay, it lets us know about how environments had changed in the past. You know, if we go to places like Wyoming and South Dakota and Colorado, and different places that are deep inland, we find coastal deposits kind of like a beach, and it lets us know that at the time, in fact, you know, for example, like during the time of the dinosaurs, there was a shallow sea in there, right? So we see that the environment has changed over 88 million years. Okay, so it's very interesting what they can tell us. It also tells us about what the climate is like. We can get a lot of climate information. You'll see this fleshed out in the class big time, about how we get different indications about what the climate has been like over Earth's history by studying the sedimentary rocks. So you got to know all this stuff. You know, I have a question, I think, in the beginning of your lecture assignment that's like, I think, if I remember correctly, maybe I'm wrong about this, but if I remember correctly, it's like, what do sedimentary rocks tell us? Well, all that I just mentioned is stuff that, you know, you should put down there. You know, that's all stuff it tells us about the past. So sedimentary rocks, okay, so if you go to a place that has sedimentary rock outcrops, take a look at this. This is actually part of the Grand Canyon outcrops. So on the bottom, you'll find sandstones that represent coastal environments. On top of that, you'll find shales that represent shallow marine environments. And on top of that, you'll find the Mauve limestone that represents a deep marine environment. So what does this tell us? How do you read this? You know, the rocks of Earth are kind of like a book, and it's all kind of in code. And part of this class, a big part of what you're going to be doing in this class, you're going to be learning to read that language, read that code about the story that is recorded in the rocks and what Earth is telling us about what's happened over the years. So what does this mean? Well, you see that sandstone is on the bottom. It represents a coastal environment. Okay? Now in the same place, eventually it became shallow marine, and it's on top. Well, sediments are laid down layer by layer. The oldest layers on the bottom, the more recent layers on top. So that means that sometime after it was coastal for a long time, then it changed and it became covered with water. Okay? Eventually it became deep marine. So later, because remember, sediments are laid down one on top of the other over time. Later, it became deep marine. So this records, the story that's being told here in the rocks is one of a rising sea. So you could see that in this particular area, the sea levels were rising, and it was getting deeper and deeper and deeper. Okay. So the kind of, you know, these are all the different rocks of the Grand Canyon, right? You don't need to know all this stuff necessarily right now. Transgressions and regressions. So what I was explaining here, right? Oh gosh, there we go. Of the sea levels rising, that's called a transgression. So the sea levels are getting higher and higher and higher, and as they get higher, you get this progression of coastal to shallow marine to deep marine sediment deposits. Sometimes regressions happen, which the sea levels back off, and you'll see as we learn in this class that sea levels go up and down, up and down, up and down, up and down, up and down. You know, sea levels are globally, well, in certain places they're dropping, but in most places they're rising, and that's part of, you know, that's a long story, right? There's There's been sea levels have gone up and down throughout Earth's history. So it's not the first time, and it won't be the last time that sea levels have risen and dropped. Okay. Anyway, that whole prelude or prologue was just kind of an introduction to what, very briefly going through things about what sedimentary rocks can tell us, and it's a lot. So let's talk more specifically about what sedimentary rocks are and where they come from. So sediment is could be a few different things. Okay, I actually mentioned 3 things here that sediment could be. Okay, a lot of sediment consists of loose fragments of rocks or minerals that are broken off of the bedrock. Okay, so you see here's the bedrock up here. All this stuff, this talus slope, this is all just sediment. Okay, even the big hunks of rock here, anything that's loose, broken off the bedrock, it's now sediment. It's classified as sediment. Okay, so this stuff is going to continue moving down the slope, moving down the hillside, and it's going to collect in a low area or a basin, and it's going to eventually become lithified and become a rock, a sedimentary rock. Okay. Now, it could be broken rock or mineral fragments. It could be shells and marine organism fragments. So it might surprise you to learn that a lot of the rocks that compose Earth's surface are composed of marine organisms, in many cases microscopic marine organisms. So it's not just shells. It's not just macroscopic shells. It's also the very fine and very small tests. I'm going to write that out. TE, just like a test, like you take a test. The tests of very small microplanktonic organisms. Now you know that the oceans are filled with plankton, which are just free-floating microorganisms, in most cases microorganisms, and it's filled with them. And their bodies, every day, they die and they float to the bottom, or sorry, they don't float, they sink to the bottom of the ocean. And they collect and they can form a rock. In fact, it's a very common way of making rocks. It might surprise you, but it's a very common way of making rocks. So that's almost 100% what limestone rocks are made out of. Okay, so that's another form of sediment. Yet another form of sediment are mineral crystals that are precipitated out of water. So this is when you have a saturated brine, a saturated fluid of some kind, and it's totally saturated with mineral content, and eventually it's going to start precipitating or leaving behind, kind of like, you can almost think of them like hard water deposits, It's going to leave behind traces of the mineral little by little. Think about if you have a salt water, even ocean water, and it gets trapped somehow in a lagoon and it evaporates, right? The water will evaporate, the water will leave, it'll go up into the atmosphere, but the mineral content is going to be left behind. So the salt and all the different components of the salt will be left behind. Okay. So physical weathering is a process that creates, or weathering in general is a process that creates sediment. Okay, it's the one that is responsible for creating this loose fragments of rocks, minerals broken off the bedrock. So all weathering means, all that word means is any process that breaks rock into smaller pieces. Okay, that's what rock means. This is, by the way, how you there's a word for this stuff. I forgot I should have mentioned this. This is called clastic sediment. Clastic. You should write that down and memorize that word. It's a very important word. Clastic sediment. Okay. Now, weathering those are processes that break down rocks into smaller pieces. Okay, and usually we're talking about, this is how we create clastic sediments. So there are 2 types of weathering. You got physical weathering. That's the physical breakdown of rocks without changing the chemical composition. So that's just when, wind abrasion, root wedging, just kind of faults and fractures, all sorts of different things that can break apart rocks without actually breaking a thermal expansion, things like that can break apart the rocks without changing their chemistry. Chemical weathering is any process that breaks down solid rock by chemical alteration. So those are things like hydrolysis, right? So the water is reacting with the rocks to form clays, and the clays kind of crumble and fall apart. There's another process called carbonation. That's the dissolution of rocks in acidic water. You might remember that I mentioned many times that calcite is very susceptible to chemical acidic attack. And so this is a way, carbonation is a very common way that calcite is broken down and limestones are broken down. There's oxidation. That's the reaction of minerals and rocks with oxygen, forms hematite. Remember I mentioned how iron reacts with oxygen to make hematite, makes rust basically, and it's a very crumbly mineral, falls apart easily, and that's how rocks can fall apart, right, and break down into smaller pieces. All those are weathering processes. So you have to have some kind of weathering process first of all to make the clastic sediment. So very common examples of these three chemical weathering processes: feldspar reacting with water to form clay, quartz, and either potassium or sodium ion that it's dissolved in the water. Okay, I've already presented this equation to you before when I talked about clay minerals in the minerals lecture. Calcite reacting with acid forms carbon dioxide gas, H2O, and calcium dissolved in the water. And you'll notice how there's a lot of this ions being dissolved in water in these reactions. Okay, so this is how ions end up in the ocean, by the way. Another one, olivine, oxygen gives you hematite plus quartz. Okay, that's yet another reaction that can break down the rock. Okay, so those are weathering processes. Jointing is a physical process. It's a process by which pressure release, when so remember in last lecture, igneous rocks, I talked about how magma bodies form deep underneath the earth, but when they rise to the surface, those magma bodies are depressurized and they get these pressure cracks, and so you can see all the different pressure cracks that form, and that's called exfoliation or jointing, and that is a common physical weathering process that breaks down the rock to form sediment. Vertical joints form while a magma cools. Think of thermal expansion cracks and things like that maybe form when you change the temperature of something really quickly. So for example, a very famous example of this is if you ever have frost build up on your windshield. Now I know that doesn't happen in Texas very much, South Texas I mean, but it does happen from time to time. Okay, you never throw boiling water on your windshield to clear the windshield of ice. If you do that, you'll crack your windshield. Okay, so it results in a very fast thermal expansion. Part of the rock expands, other parts of the rock are contracted from the cold, and you get this breakage and cracking of the rocks, or of your windshield in this case. Okay, so those are all processes that can break rocks apart to form smaller pieces. Frost wedging is another process that can happen, can break your rocks into pieces. So ice forms from water seeping into cracks and joints in the rock, and if that water freezes to form ice, the ice expands, breaks the rock apart. The same thing happens. You probably know not to fill up anything with glass and with water and put it in the freezer, right? If you fill up if you want, you can try this at home if you've never done this before. You take a water glass, you fill it with water, you put it in the freezer. The next day you will have a broken glass. It will shatter that glass apart because the ice expands. Okay, so physical weathering and chemical weathering produce sediments, and those sediments are eventually combined to form sedimentary rocks. And we classify those clastic sediments by grain size, and we classify clastic sedimentary rocks by grain size. Okay, I think I have a question about that, about how we classify clastic sedimentary rocks. It's by grain size. Okay, so the smallest types of grains are mud, okay, followed by silt. Now mud grains you can't even see; they're microscopic. Silt you can maybe barely see. Okay, it's very, very small though. It's very small to see. It's kind of at the very edge of what you can detect. Usually people can only see about something that's about 1/10 of a millimeter. So silt is barely visible. Sand, you all know what sand is. Pebbles is between 2 millimeters, 64 millimeters. Cobbles are between 64 millimeters, which is about, you can maybe think of that as maybe hand size. Boulders is anything over that. Okay, so you should definitely know you don't necessarily have to know this stuff, but you should know that mud, silt, sand, kind of the order that things go in, okay? And you should know what kind of rocks these sediments produce, which we'll go into in a little bit. So, you know, the kind of climate that you have is going to affect the weathering processes that occur. The amount of time that you have is going to affect the weathering process and how much weathering occurs. You know, the more time that weathering processes have to work, the smaller and smaller the sediment's going to become. Okay, the mineralogy is very important also to what kind of weathering is going to occur and how that's going to, what kind of sediments it's going to form. Okay, so I talked a lot about how certain minerals are more erodible and more susceptible to erosion than others, you know. So just to kind of give you an idea about what kind of minerals are very susceptible to erosion versus more stable, this is a really good graph. So halite, that's rock salt, and calcite are very susceptible to weathering. So these things will break down very quickly. Things like olivine is also very susceptible to weathering. You might remember that the more isolated tetrahedra, they have that isolated tetrahedral structure, the less interconnected the silicate tetrahedra are, the more susceptible it is to weathering. Remember though that halite and calcite are not silicate minerals. Okay, calcite's a carbonate mineral. Halite is something called a halide. These, however, are all silicate minerals. Okay, so olivine's very susceptible. Plagioclase is very susceptible. Pyroxene, amphibole, right? Biotite is pretty susceptible. Now you start to get the things that are kind of more medium to pretty tough. So orthoclase feldspars are very tough. Muscovite's tough. Clay is very tough, and quartz is very tough. And hematite is the toughest of all. You know, hematite is very difficult to erode and destroy, and you'll find that hematite is often the last thing left after a soil becomes highly leached and highly weathered. Okay, so let's talk about more of this process of how we make a sedimentary rock. That was all what I just talked about now. The last 10 minutes or so is all just like how we get from bedrock to sediment. Okay, so those are all the weathering processes. Remember, weathering is just the breakdown of solid bedrock into sediment. Okay, that's what it is. Now, how do we go from sediment now to a sedimentary rock? So the first step, like I said, is weathering. So we create the sediment. The sediment comes in different sizes, right? Could have clay, you could have silt, you could have sand, you could have pebbles, cobbles, boulders. Okay, so we have broken down solid rock and broken it down to smaller pieces called sediment. This is all clastic sediment. Okay, clastic sediment is usually composed of silicate minerals most often. So we have our sediment through weathering. What happens next? We have to have a transportation process. So transportation starts with erosion. Okay, erosion is not the same as weathering. A lot of people get it confused, think it means the same thing, and it doesn't. Okay, so weathering is breaking down the rocks into smaller pieces. Erosion is the removal of that material, where it eventually gets into maybe a river, or maybe wind, or maybe even glacial ice can pick it up. It might surprise you to learn this. I don't talk much about glaciers in this class, but you need to know that glaciers can flow and move. So glacial ice is more than capable of picking up sediment just like a river and flowing and transporting it. So this is one thing that people don't understand outside of geology, is that glacial ice flows. Okay, it doesn't slide along, it flows. It flows just like water, except that it just flows much more slowly. Okay, so that's what glacial ice was more than willing and more than able to pick up sediment and move it. Okay, so whether it's wind, water, or ice, something's going to pick up that sediment and it's going to transport it to a low-lying area. These low-lying areas are called basins. Okay, so rules of gravity work here, right? So you're always going to have sediment deposited in a low-lying area. So look how in each one of these pictures you have mountains and valleys. So the mountains are the high areas. The mountains are going to be where erosion is taking place, weathering is taking place, and it's going to move into a river system and it's going to be deposited into a valley. Okay, so these structures of sediment coming out of the mouth of a canyon are called alluvial fans. So you see alluvial fans here. This is a delta. Okay, this is a delta where a river is bringing in all of this sediment from all over the place and spreading its load into the sea. Okay, that's called a delta. Here are these mountains filled with glaciers. The glacial ice during the winter. Now see, this is a shot taken during the summer, so the glaciers have receded into the mountains, but during the winter they will proceed, they'll move out and expand, and the toe of the glacier will come all the way down here, and you can see all the mounds of sediment, huge mounds of sediment that glacial ice has deposited in the valley below. Same thing here. These are wind-blown sediments that have been moved out of the valleys, out of the mountains and into the valleys. Okay, these are all, you'll see the same process here occurring, whether it's ice or wind or water or whatever. You see the same process of the mountains eroding, producing the sediment, eroding, and it being deposited into valleys, okay, into basins. So we keep adding sediment layer upon layer into the valley. So eventually the valleys will start to fill up with sediment. Okay, so layer after layer after layer after layer after layer after layer. Okay, eventually this stuff on the bottom things are going to start to change. Okay, so the stuff that was deposited very first in the earliest part of this basin formation, the sediment's going to start to change. It's going to be compacted. The water is going to be squeezed out. It's going to get compacted together from the pressure of being buried. And there's going to be a little bit of melting called pressure melting that begins when the grains are squeezed together so tightly. So there's going to be a little bit of dissolution on the contacts of the grains under high pressure, and they're going to cement together. Eventually, water is going to flow through here as well. Groundwater will flow through and deposit its mineral contents, and that will aid in cementation of the grains. Okay, so that whole process is called lithification, or another term that you need to know for this is called diagenesis. Diagenesis refers to the whole process of taking unconsolidated wet sediments and turning them into a sedimentary rock. So all that combination of processes of dehydration, squeezing, pressure solution, along the grain boundaries here, going from all the processes combined, going from wet unconsolidated sediment to a sedimentary rock, we call that whole thing diagenesis. Okay, so you'll hear me say that word a lot. Diagenesis. You need to know what it means. Okay, so all it means is going from a sediment to sedimentary rock. All right. Another word for that is lithification. So there you have it. This is just kind of a summary slide. You have weathering of the highlands, of the mountains. You have erosion, where the sediment gets removed and transported, deposited into a basin. It collects, and diagenesis occurs, and you get sedimentary rock layers that are built out here. Okay. So you're always going to have in the process of diagenesis compaction, cementation, and lithification. Cementation is when the grains of the sediment are cemented together. Okay. Compaction is going to squeeze out the water, and often minerals like quartz or calcite will be precipitated to fill spaces between the clasts. So that's the kind of cement. Quartz, calcite, hematite, or clay even, are all very common types of cement that will cement the sedimentary rocks together. Now let's talk about specific kinds of sedimentary rocks. So the first general category of sedimentary rocks, there are 4 categories. The first category is clastic. The second category is chemical. The third category is biochemical. And the fourth is organic. The most common and most important one is clastic. And let's talk about clastic sedimentary rocks right now. Clastic sedimentary rocks are cemented clasts. So these are fragments of grains of previous silicate rock. So this is where weathering has come in and broken apart a silicate rock, whether it's could be another sedimentary rock, could be an igneous or metamorphic rock, it doesn't matter. But weathering has produced clasts, clastics, sediments, and these are going to be transported and lithified together. So sand is one type of clastic sediment, and unsurprisingly, when sand is lithified, it turns into sandstone. Okay, shouldn't surprise you. Sometimes when you have pebbles, cobbles, or boulders lithified together, usually some sand comes and kind of fills in, or maybe clay comes in and fills in the middle, and you get a rock called conglomerate. Okay, so conglomerate is made of these large hunks of cobbles and cemented all together with sand and clay in the middle of them. Okay, so clay or mud, it undergoes diagenesis, it becomes shale. Silt, when it undergoes diagenesis, becomes siltstone. Sand, when it undergoes diagenesis, becomes sandstone. Okay, a mix of different kinds of sediment, especially if they contain kind of well-rounded cobbles or pebbles, is called a conglomerate. When you have angular chunks of rock, though, it's called a breccia. So you can see how these are rather angular grains, whereas these are well-rounded. Okay, so if they're angular, it's called a breccia. If they're well-rounded, it's called a conglomerate. A common thing I will do on the test is I will show you pictures and I'll ask you, is this a conglomerate? Is it a breccia? What kind of rock is it? So you need to be able to identify these rocks, and it's not a bad idea to just go on Google Images and just put in conglomerate rock, breccia rock, sandstone rock, and just get an idea of what they look like. Now, the other kind of sedimentary rocks are biochemical. These are rocks that form biogenically from the remains of previous microorganisms, that marine microorganisms. Okay, these are things like limestone, chalk, and chert. So what all these things have in common is that they are all these rocks are composed of the bodies of microscopic organisms. So chalk, which is made of calcium carbonate, calcite, okay, are composed of what are called coccolithophores, which are single-celled plankton with carbonate shells. We'll talk more about this in the class later. All the different kinds of plankton. You're going to know all the different kinds of plankton. Coccolithophores, foraminifera, radiolarians, all this different stuff you'll know. So coccolithophores are little organisms, single-cell plankton. They float in the water. There's trillions and trillions and trillions of them. They have little carbonate tests. Okay, there's a picture of one of the tests. You could see it. You need a scanning electron microscope to see them. But they combine together. They form chalk. So the White Cliffs of Dover, amazingly, you have these hundreds of feet of solid rock. If you were to stand at the base right here and look up, you just see these hundreds of feet of rock. It's all just the bodies of trillions of times trillion, trillion times a trillion times a trillion of these little coccolithophores. I mean, it's just amazing. But every year, maybe another millimeter builds up, right? And it might surprise you that if you build up a millimeter, in 1,000 years, you have a meter. In 1,000,000 years, you have a kilometer. And that's what happens. For 1,000,000 years, these things will just be living and dying, and you'll have a whole kilometer of sediment build up after a while. It's amazing. It's deep time. It boggles the mind. We're just not used to thinking about time like that. So, it's interesting. It's almost like an illusion of eternity, or gives you a sense of eternity. It's the same way that, like, when you look at the stars or you look at the ocean, it gives you this sense of like the great depths of space, like the great size and depths of space. And I think like rocks and rock layers do the same things for time. Like, it just gives you this amazing awful kind of wonder at the depths of time, which you just see built up millimeter by millimeter every year. You get these vast cliffs made of these little buggers, coccolithophores, that are just like, how many trillions of them have lived and died over millions of years. So it's an amazing thing to think about. Anyway, back to the I don't want to get too poetic, but back to the lecture material. But limestone is made of, you can see, I mean, you can literally see the little shells and things that are in here. It's composed of, you know, little microscopic organisms, but also shells of clams, oysters, snails, all sorts of things. So it's all biogenic, biochemical. It's all created by life and marine organisms. And there's so much life in the oceans that it is able to combine. The bodies are able to combine together to give you a rock. Chert is not limestone. It's not made of calcite. It's made of SiO2 quartz, microcrystalline quartz though, so it's a very fine-grained quartz. It's actually kind of more like obsidian than it is like quartz crystal. And these are composed of the plankton of silica with silica shells instead of calcite shells. So those are, for example, radiolarian type microorganisms, plankton, give us silica like that and form chert. You can actually find a rock like this around Corpus Christi. It's pretty cool. If you go to the beaches and look around, especially in, I think, like Portland area, like more on the north side of the bay, Corpus Christi Bay, you can find outcrops of this Corpus Christi coquina, which is entirely composed of shells. It's pretty cool. It's a limestone totally made up of shells like this. But you could see how shells of marine organisms build up these limestones. These are all biochemical. Here, chalk. This is chalk from the White Cliffs of Dover. And you can see, again, where's my little pen? I can't, oh, there it is. You can see, if you were to take a microscope and look at this stuff, that's what it would look like. It's amazing, right? It's all just little bodies of little microscopic organisms, you know, that are perfectly formed. They have these beautiful little honeycomb kind of shells that are perfectly formed, but they're barely visible. It's just amazing to see that you can't even see it when you look at the rock, but when you take the microscope, you can see all of this beauty and order in the microscopic structures, these perfect little shells that compose it. The third type is organic type of sedimentary rock. So here we have coal and oil shales are the two examples I give you here. So coal is basically the ancient remains of plant life that has been basically undergone something called heat distillation. It's the same process that we take wood and we do heat distillation of wood to produce charcoal to burn in our fire, you know, fire pits or something, burn over our grills. The same thing occurs naturally, heat distillation, that takes plants, wood, all that plant matter that builds up in a swamp, actually, and it turns it into a rock called coal. Okay, that's an organic rock. Chemical sedimentary rocks are the fourth type of sedimentary rock, and they form from precipitation from a solution. Things such as that form by evaporation, for example, salt water evaporating gives us things like gypsum or halite. Travertine, groundwater, it comes from the precipitation of calcium carbonate from superheated groundwater. So that's how we get beautiful travertine tile. If you've ever seen travertine, it's a beautiful rock. It's a beautiful thing to put in your home, and it's all just formed by hydrothermal precipitation of calcium carbonate. So it's a type of limestone, but it doesn't form from life. It's not biogenic. It just forms from pure inorganic chemical reactions. Dolomite is also another. These are beautiful Dolomite mountains in the Italian, so the part of the Alps, right, in Italy, and form from magnesium-rich groundwater to form magnesium calcium carbonate. So those are all examples of chemical sedimentary rocks. They form from precipitation from a liquid. Okay. Now let's go back to clastic sedimentary rocks. Okay, so they're kind of the main form of sedimentary rocks, and there's a lot more to say about them. So we want to start to look at the shape, size, composition, and distribution of grains in these clastic sedimentary rocks, and look at what they can tell us about the conditions under which they formed. Okay, so looking really closely at the little specifics and details about the grains can really tell us a lot about the conditions, how the rock formed and the conditions under which it formed. Okay, so there are four things here. Okay, the classed grain size, the class size or grain size, that's how big the rock fragments are. the smoothness, so that's called the angularity or sphericity. Okay, I usually use the term angularity. How smooth and spherical the clasts are. The sorting, which is how similar in size the clasts are. And the maturity, the chemical maturity. That means how abundant are weathering resistant minerals. Okay, so let's talk about each of these in turn. Class size refers to how big the sediment actually is. Okay, now that can tell us a lot about the conditions under which it formed. If you find a rock with big clasts, big pieces, it means that it had to form in what's called a high energy environment. Okay? Think about this. What can carry larger pieces? Fast moving, high energy water or slow, sluggish water? So obviously the answer is high, fast moving water, right? So when water is turbulent, when it's high energy, when it's moving fast, it has a high velocity, it can carry those big pieces of rock, right? So that's where you get big pieces of rock deposited. So when you find a rock that has big, thick grains in it, sand or above, it means that the water was moving fast there. Okay, that's why when you go to the beach, you have waves, right? The more powerful the waves are there, the nicer the sand is. You know, the sand is kind of bigger. When you go to like a backwater bay or like somewhere where you're not getting a lot of wave action, you maybe have noticed that the sand grains get smaller. Like they'll start to get kind of small and more like maybe even like mud or silt. Okay, so the less movement of water, the more sluggish the water is, the smaller the grain size. Okay, the higher the energy, the larger the grain size. So it tells us about the energy of the environment. Okay, how angular the grains are tell us how far they have been transported. Okay, if the grains are very angular like this, it means they haven't really undergone a lot of transportation. They haven't been rolled. Think of a rock tumbler, right? The same process goes on with rocks, right? They're tumbling as they move either through wind or ice or water. They're tumbling along and they're getting their corners knocked off and they're getting smoothed out. So if things have been transported very far, you'll get these very spherical grains. Whereas if they're highly angular, it means that they're relatively close to their source. Sorting is kind of how similar the grains are in size to each other. This is very well sorted. This is very poorly sorted. Okay, a conglomerate and a breccia is very poorly sorted. A sandstone or maybe a clay stone or shale or something is usually very well sorted. Okay, this tells us a lot. It can tell us how the grains were transported because wind is very good at sorting. So things that are very well sorted, think of sand dunes, often are transported by wind. Water sorts things pretty well, but ice sorts things the worst. Glacial ice is a very poor sorter. So it tells us that it can tell us what the medium of transportation was. Sorting can also tell you how far grains have been transported. Well sorted means a far transportation means that it had time for sorting to take place, so it means it's been transported pretty far. Poor sorting implies a low level of transport. Okay. Maturity is a reflection of how many weather-resistant minerals are left in the rock. So if you see something that's pure quartz, absolutely pure quartz, well, quartz is really tough and difficult to get rid of. It's very resistant to weathering. All the other like crud in it, you know, the like amphiboles and the pyroxenes and the olivines and whatever have been eroded away, okay? And you just get the pure quartz left over. So if you see something with a lot of olivine and amphibole and pyroxene in it and not so much quartz, that's a low maturity. If you see something that's pure quartz, that's a high maturity because quartz is the last thing to get destroyed. That and hematite. Okay. So very mature grains have been subjected to lots of weathering and transport, whereas something like this has not been subjected to very much weathering and transport. You might remember I showed you that picture of the green sands. Remember the green sands in the green sand beaches of Hawaii? All that green sand, the olivine, that's a very chemically immature rock. Very chemically immature, I shouldn't say rock, but chemically immature kind of sediment is what I'm looking for. So that was very close to the source, right? Those olivine grains didn't come from far away. They came from right there on the island of whatever the island was, whatever Hawaiian island that happens to be on. Now, if you find something like pure quartz sand, it's very possible that quartz came from very far away. Okay, it's undergone a lot of transportation. So as you go from very close source to a very far source, this is kind of what you'll see. Breccia is a rock that almost always forms very close to its source. It has sharp edges. It's poorly sorted, right? It's got those sharp angular edges. Conglomerate is also very poorly sorted, but the big class in a conglomerate are more this really shouldn't say more angular. This should say more smooth, because conglomerate has smoother, a smoother, more spherical grain type. Okay. Sandstone, you have smaller grains. The feldspar is turned into clay and washed away, so that's undergone more transportation. Mudstone has undergone the most transportation. Okay, so close to source, you'll find breccias, then conglomerates, then sandstones, and then mudstones. Okay. Yeah, remember I use this green sand beach as an example of chemical maturity. I use this, white sand beaches here as an example of resistance to weathering and high chemical maturity. All right, we're almost done. I know there's a lot of information, lots and lots of information, but I want to end with a little section here on what are called sedimentary structures. So within sedimentary rocks, you're not only going to find information just from whatever the grains are, but you're also going to find these structures that are left over. So a very famous example of this is ripple marks. Ripple marks are very common to find in shales, mudstones, siltstones, sandstones. And just like when you go to the bay, you can see ripples in the sand. Well, those things can be preserved in the rock record, and it can tell us so much information. It can tell us what the water direction was. It could tell us maybe if it was a tidal area where the water was coming in and coming out. So it's pretty interesting. So when you have a current washing over the ripples, it's going to produce an asymmetrical. So you see how you have like a kind of shallow slope and then a steep slope and then a shallow slope and a steep slope. That is produced when you have a direction to the current. Okay, so the steep slope is going to be on the kind of the leeward side, and the shallow slope is going to be on the windward side. Okay, when you have back and forth currents like that happen kind of like more of a tidal beach surf area, you're going to have symmetric. Okay, so that's something you'll see in played out in sand dunes as well. You'll see this with sand dunes, not just ripples, but sand dunes. Okay, so there's what you all know, living in Corpus Christi, I'm sure you've seen things like this before. And here you can see the same thing played out in Dinosaur Ridge, Colorado. But this is, of course, not a modern day beach, but it was a beach at one time. And you can see how similar the two images look. Okay, so it kind of might surprise you to know there was a beach at one time in Colorado. Okay, so wind direction is preserved this way. So you'll get this thing called cross bedding. So hopefully you can kind of see this. You can kind of see these. It's a little bit hard to see in this image, but you might see these lines, faint, subtle lines, okay, that are kind of going at an angle to the main bedding planes. Okay, so here are the bedding planes, and you can kind of see lines going like that. That's cross bedding, and it indicates the wind direction at the time. Okay, so the direction, by the way, the direction in which those lines are sloping, they're sloping basically away from the wind direction. So it's pretty cool because you can look at a rock and look at the cross bedding in it, and that's going to indicate what the direction of the wind was at that time when it formed. You can also get what are called turbidites. Okay, these are currents caused by earthquakes and landslides, in which you get what's called graded bedding. Okay, so graded bedding is when you see, you might have this big disturbance, a big earthquake or a big landslide, and all of the sediment gets mixed all together, and the heavy stuff falls out of the water column first, followed by kind of the medium stuff, and then the finer mud on top. Okay, that's called a turbidity current, and they are preserved often in the rock direction, in the rock record. And it's really good because it can preserve the original direction of of up. So because a lot of times your beds are tilted, at an angle, and so turbidity currents will help you identify which the original direction of up was. Okay. Mud cracks are another thing. Mud cracks form a lot here in Corpus Christi from our kind of muddy clay-like soils, right? When it gets really dry, you get mud cracks. These things can be preserved. And again, the same thing. These are useful because it can give you the original direction of up when you have tilted or vertical sediments. Because sedimentary rocks are going to be, they're not just going to lay flat and horizontal. They're originally deposited that way, but they're going to be tilted through. A lot of times they'll be tilted throughout Earth's history. So sometimes it's not clear what direction the original up was. Fossilized scratch marks from glacial movements. Like I said, glaciers can flow, and they do flow. All glaciers flow. And as they flow over the surface, they will scratch and abrade the surface, and it will leave scratch marks. You can see the scratch marks left here, right? You can see all those scour marks. That gives us the paleo direction, the old direction of glacial movements in that area. It's pretty cool. I mean, you can even figure out what direction the ice was moving in during that time. Fossilized footprints. We get a lot of information from fossilized footprints. When I start talking about tetrapods and reptiles, it becomes really important because we get some of the first indications of terrestrial mammals this way, and terrestrial reptiles. I mean, that's another important indication of you'll see that we learned a lot about evolution of reptiles through fossilized footprints. So just gosh, it's kind of overwhelming. I'm sorry, all this information I'm throwing at you, but it's all really important, and it's all good introduction to what we're going to be studying in this class. So anyway, I hope you enjoyed the lecture, and I hope you enjoy the rest of your day. I'm going to stop here and let you digest some of this stuff. So I'll be signing out here now, and I wish you a good week.